So now I'm back from my class, and let's finish up this going over the sample 5 tests, or not the sample test, the actual test, chapter 5. So I've already talked about doing integration by partial fractions, by parts, and by trig sub. So we have one left to do, and that's by tables, and so that happens to be the fourth one. So I'm going to go to problem number 4 in here, and do this one by tables, which means I need to have my tables up here too. And I'm going to do this one twice. That's simply because there's two formulas on the table that really can help us with this to start it. Here's a sine to some power, cosine to some power, and that shows up twice. This one will reduce the power of the cosine by 2. This one will reduce the power of the sine by 2. Now, since these are equal in power, it doesn't really matter which one I start with. So I'm going to start with 11. And so sliding 11 up here, let me fold this down so that we can see 11 while we're working on it. Should have pre-folded here. All right. Okay, Formula 11 says if we have sine to the m, so m is 2, cosine to the n, so n is 2. That's going to be easy to remember because they're both the same. And Formula 11, so if I'm using number 11, then I get sine increased by 1, so that would be sine to the third x. Cosine power decreased by 1, so that would be the cosine to the 1. Over 2 plus 2 is 4, because m and m are both 2. Plus 1 less than n, well, both of them are the same, so 1 less than 2 is 1 over the sum, which is 4. Antiderivative, keep the sine to the same power, reduce the cosine powers by 2. Well, it was 2, so that goes to 0, and anything to the 0 power except 0 is 1, so I'm just going to leave it 1 dx, so I don't even have to write the 1. Well, now we have 1/4 sine integral of, or antiderivative of, sine squared. And there is a formula for that. Happens to be the very first formula on this page for sine squared. So we have all of this, sine to the third x cosine x over 4 plus 1/4 times the sine squared formula is x over 2 minus 1/2 sine of x cosine of x plus c. And that would be it. Now, if you happen to remember that sine x times cosine x is 2 sine x cosine x is the sine of 2x, you could write 1/4 sine of 2x. And you could factor out the 2's or the 4's or whatever and do some other trig subs and whatever, or trig identities, and use them to get a different answer. Now, that's using 11 and then number 1. What if I had started with number 12? So number 12 will reduce the sine by 2, and several people missed the minus in the formula that use this one, but I'm using number 12 now, redoing this. So the sine would decrease by 1, so it would be the sine to the 1x, cosine to 1 more, so it would be cosine cubed x, looking very similar. Trig identities would show that these can be shown to be equal. over 4 plus 1 less than m. M was 2, so now it's 1 over 2 plus 2 is 4. The antiderivative of sine was 2. If we reduce it by 2, it goes to 0. So sine to the 0 we're going to call 1, and cosine stays the same. So cosine squared x dx. And we have a formula for cosine squared. It happens to be number 7. And so if I use number 7, I get all of this plus 1/4, and in here I'm going to get a lot of stuff that looks similar. In fact, it's the same as the sine squared, except now it's minus, or it's plus. So it's x over 2 plus 1/2 sine x cosine x plus c. And like I said, you can, using some trig identities, you can show that this answer is equivalent to this answer. Okay, so that finishes 1 through 5. Let's do 6 now. So this area formula, if we're going to find it, we have to do this definite integral and evaluate this antiderivative. Well, fortunately, this is a pretty simple one. We could do trig sub, but a u sub for the t squared plus 3 du would be 2t dt. dt would be du over 2t. So a of x would equal, I'm changing variables, so let's actually go ahead and change the limits. You could just put question marks here and not have to change them, but if 2 is what t is, u would be 2 squared 4 plus 3, 7. 2, if I put x in place of the t, I get x squared plus 3. So that would be my limits in terms of u. And the integral would be t, which I'm hoping cancels. This I called u. And my dt is replaced by du over 2t. The t's cancel. The 2 pulls out as a 1/2, and so a of x becomes 1/2 the antiderivative from 7 to x squared plus 3 of 1 over u du, which is 1/2 ln, absolute value of u, evaluated, and evaluate goes at the end here, 7 to x squared plus 3, and I can plug this in minus plugging that in, or I can go back to x and go back to my original limits. It won't make a difference. You'll get the same answer. If I put t squared plus 3 in for the u, and then evaluated from 2 to x, I would get the same thing as if I just put these limits in, which is 1/2 ln of absolute value of x squared plus 3 minus 1/2, but I factored it out, ln absolute value of 7. And no plus c because it's a definite integral. Okay. Now we go to 7. Okay, so we're going to integrate and then take the derivative. So if we're going to integrate, it's nice to call this the derivative. You can either call it small f and use capital F. This time, that's the way I explained it in class. I'm going to do it with f of, call this f prime of t. That is a derivative, and so if I integrate it, I'm going to get f of t that I have to evaluate from 2 to x. Now, I haven't taken the derivative yet, so d dx. So now I'm going to do my definite integral here, and I'm going to get d dx of f of x minus f of 2. Now, if I take the derivative of this, well, that means I would have to take the derivative of f of x. Well, that derivative is this, but it says of x, so I got to put x in for the t, so I'm going to get the square root of x over x squared plus 3. That's taking the derivative of a function. I get its derivative with x in it. And then the derivative of, with the 2 in there, that makes this a constant, so the derivative of a constant is 0. So there's my final answer. Now let's do the other one. Now I got to take the derivative first, so I'm going to call this f of t. So if I take the derivative of it, I get f prime of t. And I don't want to do the derivative, so I'm just going to write it that way. Just call this f, and then the derivative is s prime, and I have to integrate that from 2 to x dt. So now this says find the antiderivative of f prime of t. Well, that goes back to f of t. So when I do the antiderivative of this, I get t over t squared plus 3 that I have to evaluate from 2 to x, which becomes x over x squared plus 3 square root minus, put 2 in there, and I get 2 over 4 plus 3, 7. And there's the answer to that. And now the final problem. Okay, so I said f, capital F, the antiderivative, this is the derivative, so here's the capital. I shouldn't have said, this should have been f and f. F of 2 is 8. So here's 2, here's 8. And then I'm going to find the area under here. So this is 2, 4, 6, 8 wide, down 1, 2. So the area is negative 16 and a half, negative 8. So this has to go down 8, which makes it 0 at 10. Then if I do it from here to here, I get plus 8, so it's got to go back up 8. The slope is positive, which means it's concaved up. A linear becomes a quadratic, so I'm looking for concaved up. This area, this is 4 by negative 2. So that's negative 8 and half is negative 4. So the curve went down 4 from minus 2. So going backwards, I have to go up 4, which would take me to there. This is negative slope, so it's concave down. This is 0, so I've reached a peak. And if I keep going back, this one is 2, 4, 6 by 1, 2, 3. So that's 18 and a half, 9. So it had to be going up by 9, and if I'm at 12, I'd have to start at 3 at negative 8 plus 9 makes 12. Concave down because this is sloped down. The rest of this is all 2 by 3, which is 6, negative 6. I have to go down 6, which should take me to here, down 6, down 6, down 6, down 6, constantly going down 6. So the rest of this is a straight line with a slope of negative 6.